Welcome you all. Today we are going to learn about pyrrole. It is a heterocyclic aromatic compound. I will be discussing this topic into three parts. Firstly, we will see the introduction to the heterocyclic chemistry and particularly pyrrole. Secondly, isolation of pyrrole, and finally little in detail about structure and aromatic nature of pyrrole. Let us see the introduction. Heterocyclic chemistry is a subdiscipline of organic chemistry. Till now, more than 50 million of heterocyclic compounds registered in chemical literature. It is very important topic in organic chemistry. On the other hand, it is very interesting as well. So, what heterocyclic chemistry is? Basically, it is nothing but it tells you about chemistry of heterocyclic compounds or heterocyclics. In general, the term chemistry includes preparation, properties, both physical and chemical properties, and synthetic uses of particular compound. So let us discuss what is heterocyclic compounds. Hetero means different. Next, the word cyclic means ring structure. So if the ring is made up of carbon and non-carbon atoms, that is heteroatom. It may be nitrogen, oxygen, sulfur, zinc, etc. And then this compound referred to heterocyclic compounds. Organic chemistry domains, of course, it's extended towards sometimes phosphorus and selenium also. Let's look at some examples. In these examples, the first one is benzene. In this compound, the ring is made up of only carbon atoms. This molecular formula is C6H6. So, this type of compounds are called as homocyclic compound or carbocyclic compounds. The next example is pyridine. Here, total number of ring atoms are 6. Out of 6, 5 carbon atoms and 1 nitrogen atom present in the ring. This molecular formula is C5H5N. So, we can call it as 6-member heterocyclic compounds, right? The third example is aniline. Its molecular formula is C6H5NH2. The point is here to be noted. The compound also has a nitrogen, that is heteroatom, but it is not a heterocyclic compound because the heteroatom is not present inside the ring. So we can simply say when a cyclic compound containing at least one element other than carbon within the ring system, then the compound will be a hetero compound. Let us see examples of heterocyclic compounds and discuss classification also. Generally, heterocyclic compounds are classified into 3 types: 5-member ring system, 6-member ring system and fused ring systems. In these examples, compound 1 to 3 are said to be 5-member heterocyclic compounds, since total number of ring atom in each case is 5. Out of 5, 4 carbon atoms and the another one is nitrogen, oxygen, sulfur respectively. Similarly, pyridine is an example for 6-member ring, and then quinoline, indole, indigo are the examples for fused ring heterocyclic compounds. So, the next part of the discussion is the importance of heterocyclic compounds. I definitely know that all of you must have heard about these substances: chlorophyll, hemoglobin, DNA, sugar, vitamin B12, vitamin C, antibiotics and dyes. Now we will see how these compounds related with our heterocyclic chemistry. The first one is chlorophyll. You know very well it is a green pigment present in the leaves, and this chlorophyll contains the pyrrole unit in its main structure. The next one is hemoglobin. Hemin is the blood pigment. The red color of blood is only because of this hemin, which also contains the pyrrole nucleus in its main structure. Then comes to the nucleic acid. It is very important compound in our body. Similarly, RNA and DNA, they also have heterocyclic ring system in them. The another one is sugar. It is very important in our food. They are also heterocyclic in nature. They have oxygen as a heteroatom in them. Like vitamin C also has a oxygen as heteroatom. Similarly, vitamin B12 and number of alkaloids also containing heterocyclic ring system. For example, morphine is used as anesthetic in medicinal field. Not only this, most of the antibiotics, even natural and synthetic dyes also containing this ring in it. Example, xanthine dyes. From the basis of above examples, we can understand the heterocyclic compounds are widely distributed in nature. Now coming to the pyrrole. Pyrrole is a 5-member heterocyclic aromatic compound. Example, 6 pi electron aromatic compounds bearing one heteroatom. It is a colorless volatile liquid. It is frankly soluble in water but readily soluble in alcohol. Now, this pyrrole is isolated from the natural sources. Pyrrole occurs in coal tar and bone oil. Generally, this is isolated from the bone oil. It is a commercial isolation of pyrrole from the bone oil. First of all, we take a bone oil in a big container. Then we will extract it. We will get it free from acidic and basic substances by excessive washing with dilute alkali and the acid respectively. Then this extract, which is free from these impurities of acidic and basic substances, then undergo fractional distillation from where we will get it pyrrole. Still it is impure. Then it is needed to react it with the potassium hydroxide. Then we'll fuse it with the potassium hydroxide to make it potassiopyrrole, which will then undergo steam distillation and we will get pure pyrrole. This steam distillation is done because its boiling point will come at below this water. So then here we will get the pure pyrrole. So the next part of the discussion is structure of pyrrole. On the basis of elemental analysis and molecular weight determination, the molecular formula of pyrrole is C5H5N. And the X-ray analysis shows that the planar molecule. In this slide, we have shown the ball and stick model of the pyrrole. Here, this blue color ball is a nitrogen and hydrogen is associated with this. The grey balls are of carbon compounds and these white balls are of hydrogens. Now we are discussing the orbital hybridization of pyrrole. In pyrrole, the nitrogen atom and the 4 carbon atoms are sp2 hybridized. The sp2 hybridized orbitals overlap with each other and with s atomic orbitals of the 5 hydrogen atoms, forming carbon-carbon sigma bond, carbon-nitrogen sigma bond, carbon-hydrogen and nitrogen-hydrogen sigma bonds. All these sigma bonds lie in one plane. The another point is here, each carbon atom and nitrogen atom possess an unhybridized p atomic orbital, and these are the perpendicular to the plane of sigma bonds. The p orbitals on carbons contain 1 electron each of the p orbitals, and the nitrogen contains 2 electrons, that is the lone pair electron of the nitrogen. The later overlap of these p orbitals produce a pi molecular orbital containing 6 electrons, an arrangement that is frequently referred to as an aromatic septet. So the common shortened representation of pyrrole is simply pentagon, a 5-member ring within the circle inside. The circle represents the pi molecular orbital. You know that it means delocalization of electrons. As you can see from the structure of pyrrole, we are having the 2 double bond. It resembles like diene, right? You can also must be knowing that in conjugated dienes shows this addition reactions, but this pyrrole does not show addition reactions, but it shows electrophilic substitution reactions, which are properties of aromatic compounds just like nitration, sulfonation, halogenation. It means it resembles like diene structure, but something more is there in this structure. We must discuss here the one more important point is resonance energy. In the case of conjugated diene, we have resonance energy only 12.5 kJ per mole, while in case of pyrrole, the resonance energy is about 100 kJ per mole. This also indicates that pyrrole has aromatic character. This fact ruled out that pyrrole is having a diene-like structure. This can be explained on the basis of aromatic character of the pyrrole. Since we are saying here that pyrrole has aromatic character in nature, so we should also discuss about aromaticity. For an organic compound to be aromatic, there are three criteria. One of them, it should have a cyclic structure, and the second one, should be a planar. Planar means it should have a pi electron cloud above and below the plane, and finally it should have delocalized pi electrons, and then it should obey the Huckel's rule. Huckel rule is 4n plus 2 pi electrons. That is, the organic compound should have 4n plus 2 pi electrons. You know, n is the number of an integer. Now, let us discuss how pyroles obey the above criteria. So, the first criteria is the compound should be planar. We can prove this from the X-ray studies. The pyrrole is a planar structure. The second criteria is it should have a continuous pi electron cloud. Pyrrole also should have the pi electron cloud above and below the plane, which we can see this in the pyrrole structure discussions. And the final criteria is it satisfied Huckel's rule. In pyrrole, we are having the two double bond, so 4 pi electrons are there and 1 electron is present on the nitrogen atoms. So we can say that there are 6 pi electrons. So 4n plus 2 pi electrons will be equal to 6. So this pyrrole obey the Huckel rule. From the above point, we can say this pyrrole is an aromatic compound. Thank you.